Now, maybe you're in this course because you want to ace coding interviews. And that would be totally fine, though this course is for everyone who's interested in algorithms, whatever your reasons might be. But if we're briefly sticking to that interview situation, you might get an interview question like this one. You got a list of items where every item has a value and a weight. And then you got a bag which has a maximum capacity, a maximum weight it can hold of X. And that could be any number in kilograms, anything like that. So now your goal is to write a program that basically calculates the items that should go into the bag to maximize the value of the items, whilst of course ensuring that you don't exceed that maximum bag weight, so that capacity of the weight. And here's an example with some numbers you might be getting or you might then derive on your own. A list of items, let's say, A, B, C, and of course that could be concrete items like bread and butter and whatever, but here it's A, B, C, and every item has a value and a weight. And then we have this max weight, let's say it's 8, and our goal is to derive a bag and derive what should be in the bag. And in this very simple example here, that would be the items A and C, because combined they have a value of 13 and a weight of 6. So the weight is below that weight of 8 and the value is a pretty big one. Now, we could have also just put item B into the bag, since that also has a weight of 8, so it would fit in. But with that, we would only get a value of 6, so that wouldn't be the maximum. Now, to us humans, that's a pretty straightforward problem, and we can solve this pretty quickly. But if you would need to write a program, if you would need to write code that solves that, you would probably quickly reach a point where this becomes difficult. Now, this task here is a very popular problem, which is called the knapsack problem, and it's often asked in interviews. Throughout the course, we will solve it. We're not at this point yet, but we will solve it throughout the course. But I already wanted to put it out there. That's the knapsack problem, and we'll revisit it later. Now, the question is, why are companies asking for something like this? It's probably not a problem you will need to solve when you work at Google or Facebook, right? Their users don't pack bags. Well, actually, you might need to solve similar problems. If you're responsible at Facebook for coding or for working on the part where users can create groups with a maximum number of participants and so on, you might actually have similar problems. But most importantly, questions like this are asked to check your problem-solving skills. Because as a developer, you need to be able to solve problems. You're getting hired to solve problems. And even if you're working on your own as a freelancer, you are solving problems. Or if you're working on your own private projects or on your own startup, you're also solving problems. As a developer, you're always solving problems. And with that, let's take a step back and have a look at the term algorithm. What does this actually mean, and why do we need algorithms? Now, what is an algorithm? An algorithm, in simple words, is just a sequence of steps, of instructions you could say, to solve a clearly defined problem. Back at this knapsack problem, we would have to come up with code, with an algorithm therefore, which gets a clearly defined input, which has the goal of solving a clearly defined problem, maximizing the value and keeping that weight in mind. And then you have to come up with steps that solve that problem. And that's what an algorithm is about. We have these two key parts, a sequence of steps and a clearly defined problem. And these are the two things that in the end make up an algorithm. And the same steps with the same input should always lead to the same solution to a problem. That's the idea behind an algorithm. And therefore, of course, every program you're writing is an algorithm. The entire code, all code combined in a program, is an algorithm. And of course, such programs can be split up in many smaller algorithms. If you add a click listener to a button, and on every click you add a number to another number, you also have an algorithm there. It's all an algorithm if you want to think of it like that. And as a programmer, as I mentioned, your goal is to solve problems. You need to be able to do that, and of course, you need to be able to do that efficiently, which means for a given problem, you want to find the best possible solution. And now, of course, there are different ways of defining the best possible solution. And now, of course, the question is, what is the best possible solution to a given problem? Is it the algorithm that has the minimum amount of code, so the least amount of code? Is it the algorithm that takes the least amount of time to finish, so that has the best performance? Is it the algorithm that uses the least amount of memory, so that it doesn't take up a lot of resources on the computer? Or is it simply your personal preference because you like code snippet A better than code snippet B? Well, of course, we could discuss about that. The best possible solution very much depends on the circumstances in which you're working. But often it will be the best performance you're looking for. That is typically what you would consider the best possible solution. The algorithm with the best performance, so that it takes the least amount of time. And with that, the question of course is, how do we measure performance? Because if we can't measure it, we can't judge it. Now, in order to find out what the best possible algorithm is for a given problem, we need to be able to measure performance. Now, let's see how we could measure it. And for that, let's take an example problem. Your goal is to write a function that takes one number as an input and then builds the sum of all the numbers leading up to that number. This function could look like that. It's a fairly trivial function. We get a number as an input, n, and then we have a result 0 initially. We have a for loop where we simply go through all the numbers up to n, including n. We add that to the result and we return the result in the end. We can simply write this together here. I'm simply doing this in the Chrome developer tools in the JavaScript console there, because for the moment, that's all we need. It's just a very basic first example. For the rest of the course, we will use code files, no worries. But here we could add a function, SumUp, which takes n as an input, curly braces, opening and closing, and between those hit Shift-Enter to not submit it, but to add more code in new lines. And then here we have the result, which initially is 0, Shift-Enter, add a for loop, where we have I, which is equal to 1 initially, because we started 1. We could include 0, but it makes no difference. We want to go up all the way, as long as I is smaller or equal to n. And then we increment I. Curly braces and Shift-Enter. And then in the loop body, we add I to result. And then we, in the end here, return result. This is the function that will solve this problem. If we hit enter, we now submit this function, and now it's stored here and we can use it. So for example, now we can call SumUp for 3, and I get 6 as a result, which makes sense because 3 is essentially 3 plus 2 plus 1. These are the numbers leading up to 3, and summed up they give us 6. And therefore SumUp for 4 gives us 10, because that's 4 plus 3 plus 2 plus 1. So this is the problem solved. This is our first algorithm. But how can we now measure the time it takes? Well, for that, I'll clear that. It's still stored in memory. I just cleared the console so that we have more space. For that, we can measure the time when we start and the time when we end, and simply take the difference. For that, I'll add a start variable, which is 0, and an end variable, which is 0 initially. And then here we can write start, and in JavaScript, in the browser, there is a performance object on which we can call the now method, and this gives us the current timestamp. Now I can set start equal to that, then call SumUp for, let's say, a value of 5, and then end is performance.now. And with that, we can just output end minus start. Here in the console, you can just type it like this and it will print the result. And this will give us the amount of time this took to execute. So if I hit enter here, this is the result I get. Okay, let's now repeat this. For this, you can press the up arrow key. And let's say we use 10 now instead of 5. If I hit enter, you see I get pretty much the same time. Actually, exactly the same time. So it looks like it takes exactly the same time, no matter what we enter here. Well, let's confirm this by using, let's say, 1000 as a value here. If I now hit enter, oh, okay, I get a different time. Roughly 3 times as long as it took before, right? It was 005 before, now it's 015. So it's definitely not always the same time, but it seems like there is no difference between 5 and 10. Well, that's the problem with measuring time like this in hard numbers. If we do this, we have a lot of influencing factors that have nothing to do with our algorithm. For example, and easy to imagine, the computer you're running this on matters. I'm running this on a relatively new MacBook, and of course that's a fast device. On older devices, you will see different numbers. But even on this MacBook, I don't always get the same result, because it depends on how many processes are running in the background, on the browser I use, on the open tabs in the browser, and on a lot of other things. In addition, the browser does certain optimizations behind the scenes where it caches my function and caches values, so that even for one and the same value, I will not consistently always get the same output. So measuring time like this is not a great idea, and especially for very small values like 5 and 10, it's very unreliable. Now, still, let's see it for some bigger numbers. So instead of 1000, let's run it for 10,000. And now let's run it for 100,000. And let's run it for 1,000,000. And be careful, don't enter a too large number here, because eventually it will freeze your computer. But 1,000,000 should work. And you see we're getting results here. Now let's run it for 10,000,000. That should still work. And that will be the last number, 100,000,000. Now, we see a trend at least. It tends to take longer for bigger numbers. We have this strange result for 100,000, which took longer than 1,000,000. But let's ignore that. Generally, what we can roughly say is that the bigger the number, the longer it takes. And also, roughly, especially for the bigger numbers, we can say that for 10,000,000, which we have here, it takes around 5 times as long as for 1,000,000. For 100,000,000, it takes 10 times as long as for 10,000,000. Now, if I try this for 1,000,000,000 by adding one more 0, it gets stuck for quite some time, but then again, it's roughly 10 times the time it took for 100,000,000. So it looks like for big numbers, we roughly have factor 10 when it comes to the performance, when we have factor 10 here on the number. I use 1,000,000,000 instead of 100,000,000, so that's 10 times 100,000,000. I get 10 times the performance. So this looks like the relation. It looks like if we double the number for big numbers, or we take it times 10, the performance is also doubled or taken times 10. And indeed, this is how we should look at it. We shouldn't care too much about the concrete numbers, because those depend a lot on the environment, especially if we're working on small input numbers. But we should care about the general trend, especially for very large numbers. So for this function, if we would want to draw a graph for this function, it would roughly look like this. Now we saw for small numbers it was very unreliable, but for bigger numbers we saw a linear trend. And theoretically that should be there for smaller numbers as well. There we just had too many influence factors. But generally we can say that for this algorithm, a bigger number, a bigger input number leads to more loop iterations, and hence the time it takes to execute this function increases. And for this specific function, and therefore for this specific algorithm, we saw that it seems to increase in a linear way. Especially for the bigger numbers, we could see that if we take the number times 10, the time the function takes also is essentially 10 times the time it took before. So we have a linear growth function there in the end. The factor by which we increase the input, so in this case n, is the factor by which the time the function takes increases. It increases in a linear way. And that's how we judge performance when we talk about algorithms. We don't care about the concrete numbers, but we care about the trend, you could say, about the function of time. So that we can basically make a statement about the performance of an algorithm based on the time it takes in relation to the inputs. Not speaking about absolute numbers, but about this function, about this trend, this line in this chart here. And we also call this time complexity. So in this case, we would say this sum up function and the algorithm in there has a linear time complexity. Now, of course, not all algorithms in JavaScript take linear time. We saw this here, this linear time function, but we also sometimes have algorithms that take constant time, so where the number of inputs has no influence on the time this algorithm takes. And actually, I can show you an example for constant time based on that example we just saw. Here I'm in a new tab, and now I'm going to rewrite this SumUp function in a different way, because that's typical in programming. Often you have more than one way of solving a problem. I mean, if we wouldn't have alternative ways of solving a problem, we wouldn't need to measure the performance, right? This entire idea of finding the best algorithm and of finding a way of comparing performance of algorithms, well, that entire idea would be useless and worthless if we only had one solution per problem. But of course, in programming, you can be very creative and you can find dozens or hundreds of solutions for one and the same problem if you want to. And that's why we need a way of comparing performance, which is exactly what we're working on right now. And here, previously, we solved this SumUp problem with a loop. Well, it turns out we can solve it in one line with a mathematical equation. There is a pretty nice mathematical formula that does this for us, and it looks like this. You divide n by 2 and then multiply the result of this with 1 plus n. Now this might look strange, but this is just math. And this is just a math formula, which you can derive in mathematics, that gives you in the end the sum of all the numbers up to a number. I can prove that if I save that function, if we call SumUp for 3, I get 6. For 4, I get 10. For 5, I get 15, and 5 indeed is 5 plus 4 plus 3 plus 2 plus 1. So this works, and this is just math. Now here's one important difference to the solution from before. Here we have no loop. We have one mathematical equation. Now if we try to measure this, so if I now copy this measurement code here from before, for a very large number, you immediately see this is much faster. And actually, it doesn't change much no matter which number we use. We just have this deviation based on the system we're running on. Now it even took 0 milliseconds, that's fast. But generally, you can see no matter which number I enter here, it's super, super fast and it doesn't really change. We definitely don't have a trend as we had it before, where large numbers led to a much longer execution time for the function. Now, the execution time of this function is pretty much always the same, because in there we have no iteration, we have no loop, we have just one mathematical term which is executed no matter which value we feed in for n. And that is such an example for constant time. The time it takes to execute the function is always the same, no matter which value n has. And this is not only an example for constant time. This also shows us why it's important to know about time complexity and why it's important that you as a developer are able to figure out which time complexity a function has. Because for this given problem of solving up all numbers up to n, if you would have decided that this loop solution is the best possible solution, you would have taken the slower algorithm. We were able to find a faster one after all. That's why measuring performance is so important and why you need to be able to write algorithms, but why you then also need to be able to compare different alternatives to then find the best one. Now, besides linear and constant time, we also find algorithms that have quadratic time or even cubic time, and a lot of other time complexities as well. Pretty much anything is possible here. You can have all kinds of different graphs here that grow faster or slower, but these are some of the common ones. Now we have one problem though. I mentioned that we don't care too much about the concrete numbers we got, for a good reason, because they are influenced by a lot of factors. Now still, we were able to identify some trend here. We were able to identify that for the iteration solution with the loop, for big numbers, we have a linear relation between input and time it takes to execute the function. And for our one-liner here, we saw that the time doesn't really change a lot. It certainly doesn't grow. And as I mentioned, that's important. We care about the trend, about the kind of function we have, not about the concrete numbers. And when we talk about the performance of an algorithm, we therefore could say, hey, this solution has linear time complexity, the other solution has constant time complexity. But in programming, we use something which is called big O notation, which simply makes it easier for us to quickly express the time complexity of a given algorithm to other developers. And big O notation looks like this. For linear time, you write O of n. For constant, you have O of 1. Quadratic would be on squared. Cubic would be on with an exponent of 3. And you got other time complexities as well, and you will see them throughout the course. Now we're using this because it's very easy to add this as an annotation in your code, or to tell your interviewer that this solution has a complexity of O of n, so linear time complexity. Big O notation is a super important concept. You'll find it a lot in the internet, and it's the standard way of comparing performance on algorithms. You derive the big O of an algorithm, and then you know O of n is linear, O of 1 is constant, and you know constant is better than linear, for example. So this big O notation plays a huge role and is super important when you're comparing algorithms. Now it's nice that we know about big O. Big O is great, and we care about the function, not about the concrete numbers. Now you just learned that for such a linear time complexity, we would refer to O of n. We would say this solution has a time complexity of O of n, which just means it has linear time complexity. But the question is, how can we derive this? Because the goal is not that you learn it by heart. The goal of this course, and that's important, is not that you learn about a couple of algorithms and you memorize how to solve them and you memorize their time complexities. The goal of this course is that by the end of the course, you are able to come up with algorithms on your own and you're able to derive the time complexity on your own. And of course, you could always use an approach like we did before, for logging the start and the end time and finding the difference, and then you could try to find the relation. Now, for linear time complexity, that's fairly easy. But for other time complexities, it's hard to see that relation, since you always have to keep in mind that the time you see here is heavily influenced by a couple of other factors. So you can't really rely on it to be very exact or correct, and therefore you might accidentally see a linear relationship where you just have some distortion and you actually have a different time complexity. So using these numbers in the browser is not how you should derive big O and the time complexity. The question then, of course, is how should you derive it? For that, we use a technique which is called asymptotic analysis. And it involves 3 simple steps. First of all, for a given algorithm, you define its function. Now here, I mean the mathematical function you would write to get a graph as we have it on the left. Now, of course, that gives us a new problem though. How do we define that function? How do we know which function this JavaScript function, so this code has, what the mathematical equation for that would be? Now, one important note here. I mean the mathematical equation of its time complexity. So what would be the math function be for a graph as we have it on the right here, which is produced by this JavaScript function? How can we translate this JavaScript function into a math function that produces such a graph? Deriving the mathematical time complexity functions for JavaScript algorithms sounds scary, but it isn't hard. All you need to do in the end is you need to count the number of expression executions. So with that, I mean, you look at your function, at your algorithm, and then you look at each expression, so roughly speaking, every line of code in it, and you count how often that's getting executed. Now, of course, by counting this, you will not get the real time in milliseconds or seconds this function will take. But as I already mentioned earlier, that's not what we're interested in anyways. It's way too unreliable and influenced by too many aspects. Instead, we simply assume that every expression in JavaScript takes roughly the same amount of time. If we then count the number of expression executions, so of code line executions we could say, we can easily compare that number to the number of another alternative function. That's the approach we're going to take here. Now we can have a look at that for a couple of scenarios. Let's account for n equal to 1, n equal to 3, n equal to 10, and then let's see if we can detect a pattern for n equal to anything, so to n. For that, I'll add some space here in the function because that makes annotating it a bit easier. And now let's count, and let's start with n equal to 1. How often does this first expression here execute, where we initialize the result variable? Well, I'd say for n equal to 1, this executes 1 time. When this function, the SumUp function, executes, this line here, let result equals 0, is executed exactly once. Now, how often does this for loop initialization run? And important, I really mean the initialization of the for loop, not the body. Well, for n equal 1, this runs once. We initialize this for loop once. Now, what with the code inside of the loop? How often does that run? Well, if n is equal to 1, then we initialize I to 1, we run this loop, or we run through that body in the loop as long as I is smaller or equal than 1. And if n is equal to 1, that means we execute the body in the loop exactly once. Because after that first loop iteration, I will be incremented to 2. That, of course, is not smaller or equal than n, which is 1, and therefore we'll leave the loop thereafter. And now what about this last expression? This, of course, also is only executed once. Once we make it out of the loop, we run this line. So that's the case for n equal to 1. Every expression in this function runs once. Now what for n equal 3? What about that first expression here, where we set the result equal to 0? Well, this still only runs once. It doesn't matter that n is equal to 3. When the SumUp function runs, this line only is reached once. What about the loop initialization? That also is only reached once. We only execute this line of code once. Yes, we will iterate through that loop a bit more, but the loop initialization, if we want to count it, is only executed once. But what about the loop body now? Well, this does now indeed execute 3 times, Because I is 1 initially, we loop as long as I is smaller or equal than n, and n is free, which means we loop once, then we increment I to 2, still smaller or equal than free, so we loop a second time, we increment I to free, that is still smaller or equal than free, so we loop a third time, and only then I is incremented to 4, which means we don't execute the loop again. So that's now a difference. And that last expression is still only executed once, of course, because once we're out of the loop, we execute that line, but thereafter the function is done, we don't run anything else. Now, for n equal to 10, it's similar. The first two expressions and the return statement are each only executed once, but now the body inside of the loop is executed 10 times. And therefore you can of course see a pattern here. For this algorithm, we can say that the only dynamic part is the body in our loop. And the times this body is executed is exactly the same number as we feed into this function here. So therefore, for n equal n, the three expressions here are only executed once, but the content in the loop, the code in the loop, is executed n times. And with that, we can now derive a function. If we want to express the time complexity here with t, then we could say, for the case that n is equal to n, which is of course the case we want to consider because the user is able to feed any number in, then we could say the number of code executions we get for this function is 1 plus 1 plus n plus 1. Now, of course, we can sum this up to 3 plus n, and we could rewrite this as 3 plus 1 times n. 1 times n simply because, well, just n is the same as 1 times n. And you'll see in a second why I'm writing it like this. This is in the end a mathematical function that would describe the number of code executions we have for this JavaScript function. Now, it does not describe the absolute amount of milliseconds or seconds this function takes. But as I said, that is hard to quantify anyways. But if we assume that every line of code execution roughly takes the same amount of time, you could say, if we assume that, then of course we can use such a equation to compare this algorithm to other algorithms. However, we don't even need to be that exact. After all, if you always count all code executions, you have a slower algorithm just by adding an additional line of code in there, right? Because we would have to count that, and therefore we would have a different mathematical function because we added one extra line. But of course, the big picture wouldn't really be changed. That's why we don't have to be that exact, because we don't really care about the exact number of code executions. As mentioned before, we instead care about the general function, the kind of function to be precise, the trend, the growth rate implied by that function. So therefore, when we define that function, we don't need the exact function with the exact numbers. Instead, we can generalize that. And therefore, we could also write a times n plus b. I replaced the concrete numbers 1 and 3 with coefficients. Simply because the concrete numbers don't matter. It's the big picture that matters to us here. Which kind of function is this? And this is a linear function. Okay, so now we got the general mathematical function. And no worries, we'll of course see this process of deriving the function and so on for other algorithms in this course as well. So we got this function now. Now, in order to derive this big O notation, we need to find the fastest growing term in that function. And here that's easy. That is a times n, because b is a constant coefficient which doesn't grow at all. It's always exactly the same number. A times n, on the other hand, depends on n, and for a bigger n, that term is bigger. So now that we found this fastest growing term, we remove the coefficient from that term, because again, we don't care about the exact numbers, we care about the general picture, the big picture, the general kind of function. This process here is called asymptotic analysis. Now we narrowed this down to basically this function. We can clearly see that the time complexity depends on n. Well, and that n is simply what you put between the parentheses of the big O notation. That is why it's big O of n. So with our newly gained knowledge, let's now use it to calculate the constant time complexity and see how O of 1 is derived. So here's the sum up function with this one-liner solution with this mathematical function. And now again, let's count the number of expression executions to find out how often that code runs. So let's look at the n equal 1 case and let's evaluate that one code expression we got here. How often does this run if n is equal to 1? Well, it runs once. What about n equal 3? Now, you could think this runs 3 times because we use the number n in this mathematical calculation, but that is not how JavaScript and programming languages work. If you have a loop or something like that, then the code inside of the loop is of course affected by the number of iterations. If you add 2 numbers, let's say 100 and 100, this does not mean that JavaScript has to perform a certain execution 100 or 200 times behind the scenes. And here n could simply be replaced with 3. So you would have 3 divided by 2, which is 1.5, times 3 plus 1, which is 4. And this does not mean that it runs 1.5 or 4 times. No, it still only runs exactly once. So this expression here runs once for n equal to 3. And the same is true for n equal to 10 and for whatever value you have in n. And therefore you can see if you write this as a function, t equals 1. There is no n anywhere in this. When we count the number of executions, we got no expression that would run n times. This one expression we got here runs once. So if we would want to derive big O here, then we would define the function. Well, we did that. It's t equals 1. And here, of course, there is no more general form because there is no n in it. If we find the fastest growing term, that's of course 1. It's not growing at all, but it's the only term we got. And if we want to remove the coefficient, there is nothing to remove. So t equals 1 is our final time complexity function. And as before, we take what's left on the right side of the equal sign and put that between the parentheses of our big O notation, hence we get O of 1. That's how we would derive constant time. Now, just as before, it is worth noting that it doesn't matter if you have any extra code lines in there, right? If we had another console log statement here, of course we would count 2 executions. So our formula would be 1 plus 1. Every line runs once, so we would end up with this equation. What you would do in practice is you would simplify this. So this does not lead to O2, big O of 2, but instead we would still write big O of 1, because we care about the general trend. That's why we focus on the fastest growing term and remove the coefficient here when we have a linear growth function or when we have any time complexity function. Because we don't care about the exact number of code executions in different lines, we want to see the general trend. Here it's linear time complexity, so that t depends directly on n in a linear way. And here it's O1, no matter if you add an extra line of code or not. In the end, what you want to say here, in the constant time case, is that the time a function takes to execute does not depend at all on n. And constant time is of course the best possible case for an algorithm, because it means no matter what you put into an algorithm, it will always deliver the same execution time. It has a constant time complexity, which is of course awesome and highly efficient, but I can already tell you, you will not be able to convert every algorithm to a constant time algorithm. This specific algorithm we had a look at here is an exception, where we have a linear and a constant time complexity alternative. For a lot of problems, you will not be able to find a constant time complexity alternative. But we will see those algorithms throughout the course, and we'll then of course also see different alternatives for those algorithms. Now, just to make this really clear again, we do derive these big O notations to compare different algorithms. because we can't rely on the hard numbers when we measure that, when we measure it in milliseconds or seconds. We can't rely on that. That's why we have this big O notation which tells us which kind of algorithm that is, which kind of time function it has. Now, we learned about constant time complexity and about linear time complexity thus far. For constant time complexity, n, the number of inputs, has no effect on the time the algorithm takes. For linear time complexity, the execution time grows, guess what, linearly with n. So the bigger the n, the longer the execution time, and the factor should be the same. So if you put 10 times as much n into the function, it should take 10 times longer. Now therefore, we can clearly say that O of n, linear time complexity, is worse than constant time complexity. If we have a look at those charts, we can see the same basically. For O of 1, we always have the same execution time no matter the inputs. For O of n, that's not the case. So O of n is worse than O of 1. As I mentioned before though, you don't always have the choice. You can't always come up with a solution that has O of 1, as you will also see in this course. Still, that's how these two time complexities are related. And in general, here on this slide, I will order these algorithms from fast to slow. And therefore, let's have a look at a couple of other time complexities you might see from time to time. For example, logarithmic time complexity, which would be written like this, O of log n. A graph could look something like this, and we can see that here, maybe initially it's slower than linear time complexity, but with bigger n's, it tends to be faster because it doesn't grow linearly, it grows at a slower pace instead. So the execution time of the function grows logarithmically with n. For O(n squared, we speak of quadratic time complexity. A graph might look something like this, and here the execution time grows quadratically with n. So the bigger n, the bigger the execution time, and it grows much faster than for linear time complexity. We have even faster growth, and therefore an even slower algorithm, with exponential time complexity. So 2 at the power of n. Here, this grows even faster than quadratic time complexity, and therefore, since execution time grows exponentially with n, we have a very, very, very slow algorithm, which will quickly be impossible to execute. For very low n's, you will already see problems here. Now, these are not all possible time complexities we have. In theory, any mathematical function or construct is possible. The most common ones are definitely linear, constant, and quadratic time complexity, mixed with a bit of logarithmic time complexity, and in general, as I mentioned a couple of times already, throughout this course we'll see plenty of examples also for different time complexities. Now, however, it's time for you to practice what you learned, because it's nice if I explain all of that. You really need to understand it. You really need to become comfortable with coming up with solutions and judging their quality, judging their time complexity. This is something you need to learn. Now, we will develop this throughout this course, but I already got a nice first practice for you, which you can absolutely solve with standard JavaScript skills and what you learned up to this point. I want you to write an algorithm, so write a function, that takes an array of numbers as input and calculates the sum of those numbers. Then define the time complexity of that algorithm you came up with and check if there is a faster alternative. So find out what the lowest possible time complexity, so the fastest possible algorithm, is for this problem. So if we have a look at the code, you should write some function, some numbers, which takes an array, numbers as input, and which you can call, like you see it here in the second line, and you get back the response, in this case 14 for summing up those numbers. So your task is to write this part that's inside the function and determine the time complexity of your solution, as well as the lowest possible time complexity you're able to come up with. Now for that, attached you find a little starting project, if you want to call it like this. It's a very simple JavaScript project with a HTML file, which is empty, which just imports a JavaScript file, which is also empty. And that's where you should add and call your function. Outputting the result in the console of the developer tools is perfectly fine. You don't need to do anything else. The other files you see here are just for configuring Git and for configuring my editor for recording. So you just find the index.html and the app.js file attached. You can use this as a starting project and add your solution in app.js, and we'll solve it together in the next lecture. Were you successful? Let's solve it together now. And for that, I'll add a function, sum numbers, which takes my numbers as a parameter. Of course, that parameter name is up to you. And I want to call this with, let's say, an array where I have 1, 3, and 10. And I want to console log the result of the function. So the function should simply return the sum. Now, how could we sum this up? If we knew that the array always has exactly 3 elements, we could return numbers 0 plus numbers 1 plus numbers 2. That would be a valid solution if we knew that we always get exactly 3 elements. Now, the problem is that is not something we know here. When I gave you this exercise, I didn't mention that it would be restricted to a certain length of number arrays. So you can't assume this. Nonetheless, if you could, this would probably be the best possible solution, because this has a time complexity of O of 1, so a constant time complexity, simply because we have one expression here. And for numbers, which has 3 elements, if we assume that it's always fixed to 3 elements, this still only runs once. So this here would be O of 1, constant time. Perfect. Unfortunately, as I mentioned, it's not something we can assume, so I'll leave it here for reference, but it's probably, hopefully, not the solution you came up with. Instead, we don't know how long numbers is. So let's add a result variable maybe, which initially is 0. And let's add a for loop to go through all numbers we're getting. Now numbers is an array here, not a single number. So we can use a for off loop to loop through that. So for every number of numbers, we execute the code inside of the loop. Now the code we execute in here is simply that we add number to our result. And then we return result thereafter. This could be one solution for this problem. If we now save this and we run this in the browser, I get 14, which is the expected result. Now let's also try it with a different array where I also pass 50 as a 4th value. And we should now get 64 as a result. And that's the case. So our function, our algorithm, seems to work. The question now, of course, is which time complexity does it have, and can we do better than that? Now, let's derive the time complexity of this solution. And for that, let's count executions. So let's count for numbers being equal to an array with 3 elements. If that's the case, this first line runs once, right? It's only executed once when this sum numbers function is called. It does not depend on the length of numbers. This loop here, on the other hand, runs more often than that. It runs 3 times. Now, the loop initialization here actually is only done once, but inside of the loop, we run the code 3 times because we have 3 elements. So our n here is the length of this array, because that's what determines how often this code inside of the loop executes. So that's our n. Now this last line still only runs once because it does not depend on the length of this array. Now if we have a look at this case with 50 as a 4th value, this first line still only runs once, this loop is only initialized once, and this line where we return the result also only runs once. But of course now this code inside of the loop runs 4 times because we got 4 elements, and that is what influences this code here and the number of iterations we have. So if we would want to write this as a function here, we would have 1 plus 1. So this code execution plus this code execution plus this code execution in the last line plus n in the end, right? Plus 4, but if we consider an infinitely long array where we simply have a look at n elements, this would be our dynamic part, because this part here depends on the length of the array, and that is our n in this case. So we could write this as 3 plus n, and as you learned, that is 3 plus 1 times n, if you want to write it like this. So this here would be our time complexity function. Now you learned that as a first step, we should then find the fastest growing term, and that definitely is this part here. So we would simplify to that. And then we would remove the coefficient, so the 1, so we're left with t equal n. Now, as a side note, if you had an extra line in there where you console log something, you could, of course, count this extra line, and this would execute 4 times as well. But the only difference would be that you in the end would write plus n, right? Because you have 2 n's now, basically. So you have 2n here, 2 times n. Hence, you simplify this to 2 times n, you remove the coefficient, and you got the same result. That's what I meant earlier. It does not matter if you add an extra line. It's about the general big picture. So therefore, we would write this as O of n, and that, of course, is linear time complexity. That's the time complexity we got here. Now, the question is, can we do better? Now, generally, that's, of course, not that easy to answer. You probably don't know all possible solutions to all possible problems. But let's dive into that code. Is there something we could improve? Now, for that, of course, we should focus on the part of our code that depends on n, because we can't improve this first line or this return statement. It runs only once, so there's no way of improving that. But if we could get rid of that loop, we would certainly win a lot. But to be honest, for this problem, if we don't know the length of the array in advance, there really isn't a way of getting rid of that loop. There really isn't a way of shortening this here. Now, of course, you could get rid of that for loop. You could get rid of that implementation we have here. And you could instead return numbers reduce using the built-in reduce method that comes with JavaScript essentially, where reduce takes a function, for example, an arrow function, where you then get your sum and the current number you're looking at. And you initialize the sum with 0 with that second argument you pass to reduce. And inside of that function, you return sum plus cur num. With that solution, if I save that, I still get 64 as a result. And now we have a one-liner, which is, as we learned, just big O of 1, constant time. So we won, right? It's better. Yeah, not really. This is something you could think, and if that was your thought process, I can't blame you, but it's not entirely correct. This here calls a new function, right? Now, before, when I showed you that magic function for adding up all numbers, we had one mathematical equation that was n divided by 2 times n plus 1. Now, we're not calling a function here. We have a mathematical equation here, which is solved by JavaScript. Here, we are calling the reduce method. And the reduce method, internally, will do something similar as we're doing here. So reduce will not really turn this into a big O of 1 solution, because we make our function shorter by relying on another built-in function. But that doesn't make the built-in function faster. And that's an important takeaway. Just because you were able to shrink your code down to one line does not make it a constant time code. That's only true if in that one line you're not calling a new function. Here we are calling a new function, the reduce method. So we would have to look into that reduce method and find out what its time complexity is to derive the time complexity of our function here. Now, you could do that, but in the end, I can tell you reduce will also give us linear time complexity, so this is not an improvement. Indeed, this solution we had before, where we have a simple loop where we go through all the elements, that's our best possible solution in the end. That has linear time complexity, and for this problem, we can't do better than that. And that's what I also mentioned before. You will not always be able to get a constant time algorithm. Sometimes you just have to live with linear time complexity, like in this case. Sometimes you have to live with an even worse time complexity. So here it's linear time complexity, and I hope I could make clear how we derive this and why it is the best solution here. So now we already had a quite nice introduction into the basics of algorithms, the very important topic of time complexity, and therefore I now want to give you an overview of what's inside this course in general and what the course goal is. Because this course is not an algorithm practice book. It's not full of hundreds of algorithms through which we're going to go, but it isn't that because I find it much more important that you are put into the position that you're able to solve problems on your own. You need to be able to come up with your own solutions, with your own algorithms. And this course has the goal of giving you a foundation for that. Therefore, we'll of course thoroughly look at the what and why. I already gave you an introduction to algorithms, and throughout this course, we'll always come back to this key question. Why are we doing something? How does something work? What is the approach here? We'll see a bunch of examples. Just because this course isn't a practice book does not mean that we're not having a lot of examples. We do, but we'll see a lot of examples on different algorithms, different kinds of algorithms, and also very important, different solution approaches. So different ways of solving algorithms, but also some repetition so that you have a chance of getting a feeling for a certain way of solving something, so that you have a chance of understanding how to tackle certain problems. We'll have a look at recursion, at something which is called dynamic programming, at greedy algorithms, and more. The overall goal of this course is to give you one core thing: a solid foundation and a plan on how to tackle and solve problems. Now, I want to be very clear. By the end of this course, you will not be able to solve any problem that is out there in just 5 seconds. This is not how it's going to work. Instead, this course will lay out a foundation on which you can build up on to then practice on your own, to dive into more algorithms and to understand what you're doing there, so that finally, after practicing and with help of this course, you are able to solve problems, to ace interviews, and to do whatever your goal is. I want to be very honest here, because no course can just give you that knowledge. You need to develop it on your own, but for that, you need a solid foundation, and that is what this course will give you. Now, in detail in this course, we have all those basics, and we learned about time complexity in this first module already. And that is one of the most essential parts you need to know to get started with algorithms. Now, of course, getting started is nice, and we need those essentials, but we also want to apply them. We want to dive into concrete examples. Therefore, in the next module, we'll explore math algorithms. We'll explore algorithms that have something to do with numbers, with mathematics, and where you will already dive deeper into these core concepts and be able to utilize what you learned in this first module. Now, as a next step thereafter, I'll introduce a very important concept, and that's recursion combined with dynamic programming. You'll learn what dynamic programming is and why it's extremely important when we're working with algorithms, when we're tackling problems. Now, with that new tool, with that new knowledge gained, we'll explore search algorithms and sorting algorithms, two very important categories of algorithms which you'll need in real life a lot. And we'll thereafter explore a different metric besides time complexity, which I can already say is the most important one. But besides that, we'll then also explore space complexity. Now with that, and with all that new knowledge you gain throughout these modules, we'll dive into sets and array algorithms. Sets essentially are arrays, we could say here, and you will learn how that all works and which tricky problems we might face there. After that, we had a lot of practice, we learned a lot of key concepts, and will therefore then dive into more complex algorithms. For example, the problem outlined at the very beginning of this module, and I'll give you a blueprint, a plan for solving problems and for deriving algorithms. Now, one important note here though, it might be tempting to just go ahead and dive into that last section, or just dive into the sorting algorithms section because maybe you just want to learn sorting algorithms. This is not how this course works, at least. There might be other courses which simply are practice after practice after practice. This course has the clear idea of building up a strong foundation that you have at the end of this course. And therefore, I strongly recommend that you go through the sections in order. And if you do jump ahead, be prepared to face concepts or solutions which you might not fully understand or where you need to do your own research. So my strong recommendation is that you go through the sections in order, and then by the end of the course, you will have that strong foundation on which you can build up on. If you enjoyed this video, you might be interested in joining the complete JavaScript algorithms course. You find a link below the video. Now, in that course, we'll dive way deeper into algorithms. We'll have a look at math, sorting, and search algorithms. We'll dive into array and set algorithms, and we'll dive into more complex algorithms like the knapsack problem I showed at the beginning of this video. Now, in addition, we will not just see more examples, I will also give you the tools to solve any algorithm or to solve any problem with the algorithm, to be precise. We'll dive into recursion and dynamic programming, we'll have a look at greedy algorithms, and by the end of the course, you will get a plan which you can follow step by step to find a solution for any problem. So I would love to welcome you on board the course. As I mentioned, below the video you find a link. Otherwise, I hopefully see you back in future videos on this channel.